This is easier to write, and it literally means it can go this way. But also, did you know that if you have nitrogen dioxide, that it can break down into oxygen and nitrogen monoxide? Most reactions are vice versa, okay? Most reactions are. The thermite reaction is a process of that. You could take pure iron and stuff and have it go one way. It just doesn't want to. But you can force it to. With enough heat and enough pressure, you can have the thermite reaction go backwards. Right? Remember how we had to put heat in to get it to go? You also have to put a lot of stuff in to get it to go the other way. We'll talk about that later in college. It gives free energy. I'm not going to do all that with you here. But there are some reactions spontaneous and others you have to do a lot of work to make it go the opposite way. But doesn't that make sense, honestly, if you think about it? For instance, if I put, and this isn't really a chemical reaction, but it's close enough. If I put salt in water, how much effort do I have to do to make the salt dissolve? It just doesn't. It just doesn't. How much work do I have to do to get the salt out of the water? How do you do that? Do you know how to get salt out of water? How?
You boil the water?
You boil it. You have to apply it. So, believe it or not, if you put salt in water, did you know that it cools the water down? It actually absorbs the energy and then it releases it to make that happen. So if you ever put salt in water in a thermometer, the temperature drops. It's kind of cool. Anyway, but at the same time, if you want to get the salt out of the water, you have to apply a ton of heat to pull out the water. Now that's not really a chemical reaction, but I'm using that as an example because that's how it works. Okay? And we're going to talk about the different types in a moment. I don't want to get ahead of myself. G. If there's a little g underneath of it, which most of them will do, so this is a G, this is a G, and this is also a G. Little g means that it's a gas. That's it. It tells you what state it's in. S is a solid, L is a liquid, and then this one's probably the most popular one, AQ, or aqueous. Aqueous just means it's dissolved in water. Okay? So if I had like HCl, which is hydrochloric acid, it's generally not pure hydrochloric acid. I mean, it may be, but hydrochloric acid by default is in water. That's what makes it hydrochloric acid. So hydrochloric acid would be aqueous. It is dissolved in water. The water doesn't do much to it, but it's there. We've already talked about this before. Do you guys know what delta means? I know you're reading it, but do you guys remember this from a previous lab? What does it mean? Heat is applied. The thermite reaction had a little delta over top of it. You have to apply heat to get the thermite reaction to go. Okay? And then if you see something like this, MnO2, okay? Manganese 4 oxide. If you see something like that over the arrow, it means that that is a catalyst. We had a catalyst too in our iodine. Do you remember our iodine reaction with when we had the two things and we dropped the water over it, the aluminum, the iodine? Remember it made the purple smoke bomb? Water was a catalyst. It speeds it up without actually being consumed. Okay, technically at the end the water's still there. It may be dirty, but the water's still there. Your body uses catalysts or enzymes for a lot of different things that we do in our body. Okay? Any questions, comments, concerns, hatreds, grievances, yells? How is your Shona doing, by the way?
She's doing good. She just really hates college.
Well, she chose. Is she still saying what she was doing? What's she doing?
She's doing pre-med right now.
Yeah, that's a. Of course, she's gonna hate school. You're gonna be in school for a long time doing pre-med.
Yeah.
All right, so we've got two things here. Let's practice our work. It helps us go through. Sorry, Avery, I'm calling on you. I'm so bad. What is this?
Chlorine.
Good. So?
Potassium chlorate.
Yay! Because the charge is known. Potassium chlorate as a solid can yield Of course, it's backwards, it can go backwards too, but yields, what is this, Yanina?
Potassium. Oh wait. Chloride. Oh no. I didn't think that part right.
Potassium chloride plus, yes?
Why would it be potassium chlorate instead of dipotassium chlorate? Like how there's hydrogen phosphate and dihydrogen phosphate.
So it's not a subscript.
Yeah, the two
Oh,
here,
it's okay.
this is two of that. Remember, the coefficients are important, don't get the confused subscripts. Chlorate's only -1, so a potassium oxide. Okay? Reacts to make an oxygen gas. Okay? This is a reaction. It also means that vice versa, potassium chloride and oxygen gas, if pushed back the other direction in equilibrium, can create the other thing. Okay? By the way, though, it says if it's heated, which means up here, there should be a delta, and it says iron 3 oxide. I should also have Fe2O3 up there as well. Okay? I love how they give the example, but they don't put those up there. Okay? Alright, let's try this. Let's have some fun. Let's do this for real. I'm not going to try to pick on you or make your minds melt or do things the wrong way on purpose anymore. Okay, here we go. What do I got? What's the first thing?
Solid iron.
Okay, what is iron? Just that big. Iron is not normally diatomic, right? We already talked about which ones are. Solid iron and, oh, I forgot to put solid. Man, boo-boo on my part. Solid iron and, yes, chlorine, if it's going to be a gas, is always Cl2. Solid iron and gaseous chlorine react to form what? Yeah, what is that? It's not Fe2. If Cl was a -2, it would be. So what's the charge of iron? Hey, what's the charge of iron? What do you mean? What's the charge of chlorine? -1. Flip them. Powder is a solid. I think we all agree that that's a solid, right? Right? Powder is not something that's gaseous. I mean, even if you throw it in the air, it's a powder. What does it do? It falls down. It's a solid. Okay? Write the balance equation. So Fe plus Cl2 yields FeCl3. All right, what do we got on this side? Susan, how many iron over here?
I can't see it.
Is there a number in front?
No. 1.
Good. Is there a
What?
number in front?
Is that G? Is it after G?
It's FeCl3.
I mean,
That's an
what's
S.
after?
That's an S for solid.
Oh, it's a G.
Solid
Oh, solid.
gas.
Yeah, that's G.
You can also move up a little bit, Susan. There's no one up here.
Okay, thank you. I just cannot.
She's like, thank you for the offer. No. All right. All right, so we have how many Fe over here?
1.
Good. All right. Ian, how many chlorine?
2,
Yes. Don't forget the subscript. How many chlorine over here?
3,
Do they match?
No.
Okay. Colin. No, I already called you. Avery. What doesn't match?
The chords.
The chlorines don't match. The chlorines don't match. Sorry, that was an old joke. All right, moving on. So if they don't match, what could I do? We could look at common multiples, but I'm not even going to do that with you. What do we need to fix to try to make this work?
Make Fe be 2 and the color, the first gas be 3, and then the last one 2.
Look at Susan just mentally solving the problem,
Yeah,
not step by
whatever she
step.
said.
Avery, walk us through what you think she just said. No, you can do it.
No,
I believe you. Okay, so we talked about 2 and 3. What's the common multiple? Okay, how can I make both sides 6?
we can make it 3 chlorines.
3 right here? Okay, so that's gonna make that 6.
And then 2 chlorines on the other side.
Alright, so put a 2 here. Now you can't split it, this is
Yeah.
one thing. So this is gonna make 6 chlorines. Uh-oh. But it makes 2 iron. Did you mess up?
Yeah.
No.
No. No.
Can you fix that now?
Yes.
How?
Um,
Go ahead.
you can make it 2.
I can. Hey, that's it. You didn't mess up. Sometimes there's steps. Sometimes it doesn't work. It's all right. It's how it works. Don't give up if it doesn't work the first time. You probably have to add something else to it. Okay? 2 iron plus 3 chlorine gas molecules make 2 Fe3 chloride. Iron 3 chloride. Was it that bad? No. That's right, Avery. That's why you're gonna volunteer to do the next one too, right?
Right.
She's like, Alright, let's do a fun one. This is a reaction that Mrs. Matthews is gonna do really soon. I gotta make sure I've got good stuff back there, because it's over a year old. It probably isn't. She's gonna get mad at me. Hydrogen peroxide decomposes naturally, which is why I said it's probably not good, because it's been a year.
Water.
It decomposes into water and oxygen gas. Which is why if you pour it on you, you have an enzyme. Actually, we can just put the enzyme up here. Catalase. We have the enzyme that our skin produces called catalase that automatically speeds this reaction up, which is why if you put hydrogen peroxide on a cut, you see it start bubbling almost immediately. If you just put hydrogen peroxide out in a bowl outside of the sunlight, it will do this too, it just takes all day. But if you put it on your skin, our skin can speed up the process 100-fold. Okay? Let's balance it. Jenna, how many H's over here?
1, 2.
2 H's. How many O's? Oh, that's easy. How many H's? Yay! How many O's? Oh, no! Jenna, how dare you? You have led us astray. What can I do? What doesn't match? Yeah, so we could do this a few different ways. We can do this step by step, okay? But our O's do not match. Which side has less O's? Yeah, so we need more O's there. Now we could try to multiply it by the different things, like I said, the common multiple and stuff like that, but we just need more O's on the other side. So what's a way to just increase the numbers on the other side? How can I make more O's over here? What can I put in front? Just another number, so instead of 1, yeah. If I do 2, that's gonna give me 4 H's. It's gonna give me 4 O's. Well, darn it, Mr. Hill, you just jacked us all up. We don't even have any. Now all the numbers are wrong. What can I do next time? I would start with H's. 2 where? Yeah, I can put 2 here. 2 is 4. 2 times 1 is 2 plus 2. The only way you get better at this is to practice. But I promise, once you find your groove and what works for you, you can just do these crazily fast. Okay? Do another one. I am making these up as I go. Let's do. Okay, here we go. You don't need to know the name of this. Propane gas plus oxygen when heat has been applied, aka a spark, creates carbon dioxide and water. This is a normal combustion reaction. Combustion reactions where you literally burn something and go through that. In fact, with the time that we have, let me go ahead and do that for you real quick. I'll change it later. This is pretty close to that, but it's not going to be exactly what I wanted. Emily missed a bad day. I'm just getting it ready, just so you know, we're not gonna do it right now, I have to wait a few minutes. This is isopropyl alcohol, okay? It has a boiling point of like 82 degrees Celsius, so it's like 180-ish Fahrenheit, but it's volatile, means it evaporates easily. I can light this on fire. In fact, you guys have seen that before. I literally just put it in there and it just burns, okay? So I'll just go ahead and do that, why not? I think I have matches, where did I leave them?
Underneath the tissue.
Underneath the tissue.
Oh, look, the funky wings.
Where's that card?
Tissue box.
Oh, what are the wings in this? What
That was not it.
is this?
Hold on. Oh, here they are. I can take this, I can put it right here.
Oh,
This is
This is-
like what it's in here.
Yeah, I'll put a little bit more. Yeah, yes, this is not what's in there. I can strike a match
You had like hand sanitizer fire?
and I can
That would smell so bad.
It's really good.
I can make a fire. Okay. Now this is it's a combustion reaction. It's not combustion. We'll talk about that in a second. This is just burning the fuel. The fuel with the heat applied is literally taking the alcohol. It's breaking it down into carbon dioxide, which is what we breathe out, and there's water. Do you see water?
In the air.
It's as a gaseous form. Fires are hot enough, but there actually would be hotter if there wasn't water there. Because half of the heat is actually to make the water, as soon as it's created, into a vapor instantly. I don't know if you've ever seen the movie. Have you ever seen the movie The Martian? It's got Matt Damon in it. It's about going to Mars. There's a book about it too, by the way. You could read either or. One of the things he does is he needs to make water for his potatoes. So he gets hydrogen gas and oxygen gas, that's flammable, and he starts a fire with it, and he puts like a little tarp around it. As the fire burns, the gaseous water hits it, condensates, and drips down so it can make.
Hydrogen and oxygen.
What?
Where does he get the hydrogen and
He
oxygen?
had tanks, because he has to breathe oxygen and hydrogen for jet fuel. And he can make water that way, because he was trying to grow potatoes on Mars, okay? Now, that was a normal burning reaction. Fun, whatever. Well, let's get to this first. What's in here?
Air.
Yes, good job.
And the
Oxygen. This may look like it's empty. Oh, there's a little water in there, but it's not that big of a deal for what we're doing. It may look like it's empty, but it does have air in it. It has oxygen in it. Okay, it's got carbon dioxide in it too, which will not help us, but in this case, whatever the case is. I'm gonna go ahead and pour some of this in here. Not too much. Now, I'm gonna hold on. What I'm doing is that alcohol that I have in there, I'm just gonna keep swishing it around for a few minutes. All I'm trying to do is allow it to be volatile and make a vapor. When it's a vapor, this is where we get true combustion. True combustion is where instead of having a fuel and having the air have to go to it to burn, how long did that fire last? 20 seconds, maybe 30, I don't remember, okay? If I poured this much on there, how long would it have lasted? Probably about a minute, maybe, because I poured a little bit more in here. My goal here is not to make this burn for a minute. My goal is to have an evenly mixed with oxygen so it all burns at one moment. This is how your cars work. We'll talk about this later because I'm actually giving you a precursor to our lab. That's what I'm doing right now. It gives us a nice mixture of the oxygen and this liquid so that it mixes nice and well and that this air is covered in both isopropyl alcohol and oxygen everywhere. So if it were to catch on fire, instead of it burning slowly, all of it ignites at one time. It's literally how your car works, it's how the engine works. Instead of doing it this way though with a carburetor, which is what we used to do, we now use fuel injectors to inject a spray of gasoline. It's a spray so that it's aerosolized, so that way it automatically can, and bam, at one shot. There's a lot of power in combustion. Now, we give this another second. A little bit of an old match head in there. Now this is still not going to be perfect. One, because isopropyl alcohol is not a great fuel. You're just a little closer though. You can say that, you'll be fine. I don't ever feel like Jenna actually believes anything I say. I'm like, you can be there, you'll be fine. And she's like, I don't want to be here anymore. You don't have to hide. Your hair is going to catch on fire. Okay, here we go. You saw my other reaction. This may make a loud noise. I'm actually counting that it will. All right? Ready?
No. Yeah.
The whole thing goes at one shot in a quick reaction.
That was insane.
Now, with that being the case, anyone want to feel the top of it? It won't burn you, not right here. Right? All that heat was released at one shot. Anyone else? Anyone? Just warm. It's not. You can tell the reaction. Okay? Did you see the difference between the two? Right? What was the difference? Why? I just say back what I said earlier. Why?
Why what?
Why was that faster? And why was it?
Because oxygen was mixed throughout.
Oxygen was mixed throughout. It wasn't just burning here and oxygen had to come to it to burn, that's what makes the fire burn. So if there's more oxygen, it would burn faster and hotter. But if you have all of that air locked in there, where it's all mixed together evenly, when you light it, within what, maybe I'd say maybe a second and a half, maybe, all the fuel is burnt up. What do you notice about the inside of this now?
Water.
There's a lot of
Condensation.
water in here. This is not extra fuel that didn't burn. This is water. Because when you burn, you create water vapor. And a lot of the vapor is in here. You can see that it's literally like there's water at the bottom, but you can see how foggy it is in there. There's a lot of, yes, Susan.
What if you put the fire in again?
What if I light another fire in there?
Yeah.
There's a little fuel in there. I might be able to get it to go off again. But you know what the big limiting reactant's gonna be? Yes, the fuel, there may be some fuel in there, but what did I just get rid of? Oxygen. This is probably loaded with carbon dioxide. So I'll try it. It might whoosh again. I'm not saying it won't. There's a little bit of air probably got in there. Let's see what happens. Match might even go out. See, look, do you see it's burning right there at the top only? Do you see that?
Yeah.
Whoa.
Wait, that's way.
I didn't want to get too hot because I don't want to melt my jug. Okay? It's hot. Just making sure it's cool. Okay. I don't want to be too hot because there is still fuel in there, right? So if it's too hot, I don't want to just go and off and I'll be teaching all of a sudden it goes whoosh, and then Jenna dies, like immediately from a heart attack. You know? Okay? Cool.
I smell the alcohol.
Have you ever seen so isn't that kind of cool that you can see the carbon dioxide literally not letting it burn down there? And remember, it was only burning here. If I got everything out, the little bit of fuel that's in there, maybe, right? Anyway, oxygen is what we're at. Also, if you had a fire and you tried to put it down there, it would smother down there. All right, I'm done. I'm talking too much. Oh, they took my hose.
Hey, Ian, isn't the
How am I
math
supposed
thing
to
due
do
today?
this? You just scribbled and started like extra code, right?
Yeah.
You're not even in our sound.
Very aware. No, I just.
You found the hose.
I heard Jenna talking about it. The thought process.
Ian,
Oh, I forgot.
we have a Spanish quiz thing, right?
Yeah, I'm gonna do that in history. I did half of it.
Yeah, I'm gonna just do it.
At the end, I forgot about you. You had that carpenter.
Like the last couple times.
So there's no reason for us to have
Because it
this?
was aired.
The whole class is online. There's technically no reason for this. Honestly.
This is aired.
But why should we have it in the education meeting? Why should we have them in education?
It's helpful to either ignore it while, you know, like, wait, how are we gonna do this? I mean, I think we can.
The discussion
You didn't
questions.
say while he teaches.
The discussion questions
He
due.
said while we're going over, so I assume it's like